In this video, we will explore how to compute electromagnetic wave resonance frequencies in closed cavities. We will consider a given cavity size for the 2.25 dielectric permittivity, and we expect analytically to get exactly 5 GHz for the TE10 mode. Okay. So let's go. Let's create our box of given sizes that will provide us this 5 GHz resonance frequency. There we go. Now we can assign material properties. Here we will pick air everywhere, and then we will tune the permittivity to use 2.25 relative permittivity. And then we can move on to the physics, where we add electromagnetic waves, and we add perfect conductor condition all around. So what this will do is that it will set the tangential component of the electric field on all these faces to 0. The perpendicular component at the face is still allowed to be non-zero. This is a perfect conductor condition, and on the faces you only have access to the tangential component, so this effectively sets indeed the tangential part only to 0. Now we can move on, run the simulation. So we could set the mesh size to something that is fine enough to be close enough to the 5 GHz we should get, and we can start meshing. And in the meantime, we can set the analysis type to eigenmode analysis. We could ask for 5 eigenmodes, and then as a last step, what we need to do is we need to ask for the target, to provide the target eigenvalue magnitude. So we want to target something around 5 GHz, so we could actually target 5 GHz. So the eigenvalue corresponding, it's the square of the pulsation, so that's the square of 2 pi f, where f is the 5 GHz. You do the math, this is what it is, very big number, the square of the pulsation. And then as a last step, we could ask to see the eigenvalues and also the electric field, and we can run the simulation. Yeah. So this should be soon finished. And we can see a bunch of resonance frequencies, but we will see it's the E10 with electric field in the y direction. This resonates at 5 GHz. With a finer mesh, you can get even closer, but this is more than enough. Now we can also visualize the results. So we could visualize what this first mode looks like here. And we could as well, you could check all the other modes as well. But what we're going to do is we're also going to use the glyph filter, and for slightly smaller vectors, we will see that the electric field is indeed in the y direction, as you can see here. So you can see that the perfect conductor boundary box is enforced, so there is no tangential component, or it's the 0, the tangential component at the skin of the box, but the perpendicular component can still, of course, be non-zero. So this concludes this video, and we hope to see you in another video.